Good afternoon to all of you. In the last tutorial, we saw some problems on first order circuits. In today's tutorial, we'll see some problems on second order circuits. Okay, so the first problems goes like this. A switch is kept in open position. So the figure is given out here. It is kept in the position 1, that is, it is put into the top contact out here for a long time and toggle to position 2 at t is equal to 0. So once it is kept in the top position, you have this voltage source and you have a resistance, inductor and a capacitance in series. So it is an RLC series circuit which is powered by an voltage source. Okay, and the values of R, L and C are given here. It says calculate the characteristic roots of this circuit. Okay, so the characteristic roots is to be calculated, and also from that root we need to comment whether the circuit is overdamped, underdamped or critically damped. Okay, so we need to find out first the characteristic roots, and for that we need to compute alpha, which is the damping ratio, and omega 0 or omega n, which is the natural frequency, and the formulas for RLC circuit. Alpha is given by R divided by 2L and omega 0 is given by 1 by root LC. Right, so this I had explained in the theory class also. These are the formulas. So by putting the values of R, L and C, so we get alpha and as 5 and omega 0 as 1. Right, in this alpha is known as the damping factor. Okay, because that is the one which is going to kill the oscillations in this circuit. So e to the power of minus 2r, r divided by 2l. So r is in the numerator, that I explained in the class, because as the current moves in this circuit, I square r will be heat will be generated, and that will consume the energy which was stored as charge in this capacitor. Okay, that is why r is in the numerator out here, and L is in the denominator because L will oppose the current in this circuit. So that will the larger L will prolong the damping of this circuit. Okay, so that is the reason L is in the denominator and R is in the numerator. This derivation we have seen in the class. Okay, so with that straight away the roots are given by S1 is equal to minus alpha plus root of alpha square minus omega 0, and S2 the other root is given by minus alpha minus. So this becomes plus and minus. So it's an quadratic equation. So you get two roots. Now if you see this within the root will be slightly since it's 5 square minus 1. So the result of this root of 5 square minus 1 will be slightly smaller than 5. Same here. So you get two roots which are both negative, right? So since it's both the roots are negative roots, and also they are not, there is no imaginary part in S1 and S2. They are both are going to give you negative real numbers. Okay, so the we know the roots, and the final equation is given by a1 e to the power of s1t and a2 e to the power of s2. So here if you see s1 and s2 both are going to be negative real numbers. So that is the reason we say that it is overdamped, right? That I explained in the class, that if both are negative, so if you see both are an exponential dying signals, so and since it is just going to slowly go, the signal is going to, there will be no oscillations because there is no imaginary part here, so there will be no oscillations. It will smoothly go, and it will eventually it will settle down to the final value. In this case the final current and voltage will be 0 in this case, because the whatever is the energy that will get dissipated. So this is the problem. So it is an overdamped system because they are both are negative, and this is the characteristics equation. For the second problem, it says find IT for t greater than 0. So I is shown here. Right, assume that the circuit has reached steady state before the switch is opened. So the switch is initially closed out here. So then we need to find out the at t is equal to 0. So it is closed for till the currents are reached steady state. That means it is closed for a long time, where steady state condition is reached. That is the capacitor is charged to the required voltage, and the voltage across inductor is also 0. That means steady state. Okay, that's the steady state which is The first, for all these problems, the first thing is to find out what is the initial voltage across a capacitor and the initial current through an inductor. So for all second order, or even for that matter first order circuits, okay, the process will be like this. First, find out the initial voltages across the capacitor and initial current and the inductor. So in this case, if you see, the switch is closed position. So what would be the current flowing through the 0.5 ohm inductor? So this capacitor is an open circuit out here. So current would only flow like this, in this manner, and that current will be 10 divided by 6 plus 4, right? So it will be around 1 ampere currents will flow through the inductor. So if you see, I is equal to 10 divided by 4 plus 6, 1 ampere current. So that is the initial current in the inductor. And what would be the voltage across the capacitor? So if you see, there is no current flowing into the capacitor, it's in steady state condition. So the voltage across the capacitor will be same as that of voltage across the 6 ohms resistor, because there is no voltage across the inductor also in steady state. So what is the voltage across 6 ohm? So it is voltage is equal to the current which is 1 ampere into 6 ohms, so you get 6 volt. So this is how we for all these problems we need to first find out the initial condition. So in this case, the initial condition is 1 ampere current in the inductor and 6 volt, that is the voltage across the capacitor. Having done that, then the next step is to find out the equation. So once it is opened, you will find this is the only loop which is available. So whatever is the current flowing was initial current which is flowing into the inductor, the moment you switch it off, so that current will continue to flow in this loop now here, and whereas this voltage will initially be whatever was the voltage stored across the capacitor. So those two initial conditions will be there, so there will be no discontinuity. So that this circuit will try to maintain that current at t is equal to 0 and that voltage across this capacitor and I0 in this small loop. So this is the equivalent circuit for t greater than 0. Now since it's a single loop, you can combine this 6 ohm and 3 ohm and replace it with a single 9 ohm resistor. Right now again here we need to this is an RLC circuit series. So alpha is equal to R divided by 2L, which comes out to be 9, and omega 0 is equal to 1 divided by root LC, which comes out to be 10. Now with that you can find out the two roots. Now if you see here, S1 and S2, whereas this is 9 square minus 100 and 9 square minus 100. So if you try to find out the root, so there is an this is an imaginary number is available here, right? So what does it indicate? Like we read in the theory class, then it means there is going to be an oscillation in this circuit. Okay, so whereas this is the damping factor out here, but still since there is an imaginary component out here, it is going to oscillate and then come to and that oscillation will slowly come to 0. Okay, so the equation will be like this: e to the power of minus 2. This is the one which is going to damp the circuit, and this 4.39J, okay, that is the one which will result in oscillation. So we can write an cos and sin A1 and A2. So there are now two A1 and A2. These are the two variables which we have introduced here. So we need to find out these variables. That we can do by putting the initial values in the circuit. So this is what this, if you see the red line, this is what is going to happen. It is going to oscillate. So there is going to be an oscillation in this circuit. Okay, now this is the equation which we got. Now we need to put the initial condition. So the initial condition is first initial condition is t is equal to 0, I is equal to 1 ampere. Okay, that we found out here, right? If I go back here, I 1 ampere and capacitance voltage is 6. So these two initial conditions we are going to apply here. So let's come back here. So at t is equal to 0. So in this equation, if I put t is equal to 0, this thing will become 1. And cos 0 is 1, whereas sin 0 is, so only thing which will remain here is A1. So A1 is equal to 1. And now again we can differentiate and if you find the loop voltage here, it will be L di by dt, right, plus 9I, right, R into I, and plus V0 is equal to 0. So di by dt, and I bring the L in the bottom out here. So it is that is the voltage across this inductor, right? I have found out the equation for inductor current here. Now I am writing L, I am bringing it here. So this is L Ri minus V0. Okay, now where did I get this minus 6 from? Ri is the initial current is 1 out here, right? And this resistance is 9. Okay, 6 plus 3 9. If I see, this is the equivalent circuit. So 6 plus 3 9. So this becomes 9 and minus voltage across the capacitor, which is which we know it is 6, right? Initial condition, the voltage across this was 6. So 9 minus 6 will be 3, right? And that inductor minus L is 0.5. So you get 6 ampere per second di by dt, right? So why we are finding di by dt is because we can differentiate this. We are trying to find out A1 and A2, right? So A1 we already found. To find out A2, we are going to differentiate di by dt out here. So that is why we are finding di by dt. And what is this equation? This is only the di by dt. L di by dt is the voltage across the inductor. That we can write is as minus R I0 minus V0. Okay, R is a combination of series combination of 6 and 3, and V0 is the voltage across this capacitance, right? So and we are bringing that L here. So this L di by dt is nothing but voltage across the inductor. So we get minus 6 ampere per second. So we are going to differentiate this. We are going to write this after differentiation, and then substitute at t is equal to 0. The value for t is equal to 0. So all these sine terms will vanish, cos terms will become 1, and then we put these values and we get the value of A2 here. So finally in this equation A1 and A2, A1 is 1, and from here A2 is 0.6882, so we put that. So we get the final value of IT here, right? So let's take on one more problem. Okay, now in this problem it is slightly different. Here the switch has been closed for a sufficiently long time here, and then at t is equal to 0 it is open. So you are going to throw it open at t is equal to 0. Okay, so here also the first and foremost thing to do is find out what is the voltage across the capacitor and the current in the inductor. So if you see the current, okay, initially the switch is closed out here, so this capacitor will be open. So the current into this inductor, so everywhere we need to find out two things: currents in inductors and voltage across capacitors. So the current in this inductor in this case will be 12 divided by 5 plus 1 6. Okay, so 2 amperes. So that is the current which is going to flow in this. And what about the voltage across capacitor? So voltage across capacitor, we can use the potential divider rule. There will be no voltage across L because it is steady state condition. So you can write 12 into 5 divided by 5 plus 1, right? So you'll get as 10 volts. Okay, that is 12 into 5 divided by 6. Okay, so 12 6 that will give 2, and into 5 will give 10 volts. So this is the initial voltage across the capacitor. Now once the switch is thrown open, right, now what is the condition? So it is again a RLC circuit, but there is a voltage also in series of this. There is a voltage also in series of this. So the voltage across the capacitor now, okay, that we can write it as VCNT. Okay, VCNT means because of the natural response. Natural response is without considering the voltage source. If RLC is there, then what is the natural response? And then forced response. Plus VC forced response. Forced response is because of the voltage which we have applied here. There will be an so if there is no 12 volt out here, then it will be just natural response. Since there is a 12 volt source also, it is known as, so we need to have a force response component also. So we need to find both these things. Okay, so this we found out initially itself, 2 amperes current and 10 volt. Now if you see, now in the first case, okay, this is the differential equation which we know for it is an RLC circuit, right? So we need to find out an alpha and omega n, right? So alpha n is R divided by 2L. So what is R? R is 1 ohm, and L is again 0.5 divided by 2. into 2 here in the denominator. So you will get alpha is equal to 1, and omega n, again omega n is 1 divided by root LC. Now L is 0.5 and C is 2. Again you will get alpha and omega n both to be 1. Okay, that means the roots are equal. So the equation will be a1t plus a2 e to the power of alpha t. Okay, this is taken from a different textbook, so the notation is slightly different. We learnt it as e to the power of st. Okay, st. So here s is equal to s1 is equal to s2 equal to minus 1. Because if you have seen that equation here, let me go back here. Where is that equation? Here S1 and S2, here alpha and omega are same, so this becomes 0, this becomes 0, so S1 is equal to S2 is equal to minus alpha, right? So yeah, here, so this is alpha written because this is taken from a different textbook. It will be S is equal to S1 is equal to S2 is equal to minus alpha, whereas alpha is 1, so you get a minus 1 here, right? So the equation will be VCT a1t plus a2t e to the power of alpha t. Okay, alpha is st. Okay, that is minus 1 and 2t, right? And then plus a. What is this a? Because in this case you have an forced response also here, which is an power 12 volt is given here, right? So that is the reason we write an a out here. Okay, so because there is a forced response. So now if you see at t is equal to 0, we apply the initial conditions. Okay, at t is equal to 0, what happens? So t is equal to 0, this vanishes, this term. A2 t is equal to 0, so a2 remains. So A2 and this A also remains. So A2 plus A is equal to 10. So initial voltage across this capacitor is 10, right? So you get an one equation out here between defining relation between A2 and A. Now for the second relation, we do a derivation of Vc by Vt. Now if you see here, CVC by dt is nothing but current, right? Charge is C into Vc, so the current will be C dV by dt, so I0. So if you multiply it with C dV by dt will be I0, which is 2, because if you see when this switch is thrown open out here, whatever was the current in the inductor, that will be forced into the capacitor. So the initial current in the capacitor is same as that of that in what was there in the inductor before just opening of the switch. Okay, so we'll see in some other cases it will not be the case. Here whatever is the current in the inductor, there is no path for it to follow, so it will go through the inductor. There is no way out here. So the initial current in the capacitor will be given by the steady state current of the inductor itself, which if you see here, the steady state current was 2 here. Now the capacitance value is 2. Okay, so that 2 and this capacitance C value gets cancelled. So you have DC dVc by dt as 1 volt per second for t equal to 0. So if you substitute that, if you do a derivation of VCT, which is given here, and then substitute the value out here, so we get one more relation between A1 and A2 as 1. Okay, so this is first equation, this is the second equation. And we can also find out the third equation, which is nothing but Vc infinity. At t is equal to infinity, this switch is thrown open here, so the capacitor will get charged to 12 volt. Okay, so at t is, if you put t equal to infinity in this equation, you get one more equation, which is t is equal to infinity. So this whole term goes to 0 because it is a minus 1 out here, so this becomes 0. So you get an A as 12. So now you have 3 equations. With that you can find out the value of, this is the one equation, and earlier we got one equation out here and the second equation out here. So substituting these values, we can write the equation for voltage. Now to find out the current equation, it is C dV by dt. So you differentiate this equation which we got, differentiate it once and multiply it by 2, which is the value of the capacitance. So you get the current equation. Now if you see in this current equation also, it is exponentially dying off, because once you have switched it off, the current has to slowly come to 0, because once the capacitor gets charged to full 12 volt, the current will be 0. So you can verify your answer that way. If you have made a mistake, if you know what is the steady state condition, then you can verify your answer. Here it will come to at t is equal to 0, the t is equal to infinity, this becomes, and also at t is equal to 0, if you want to verify it, this becomes 0, so it will come as 2 ampere. Okay, that is the same condition out here, so you can verify your results that way. Okay, so let's take one more problem. So in this, the switch S1, okay, is was closed in position 1. It was kept in position 1 for sufficiently long time, and then kept in position 2. Okay, after keeping it long, you are throwing it to position number 2. Find the voltage VC. Okay, expression for the voltage across the capacitor and the current across the capacitor. Okay, for t is equal to 0, and the value of the capacitance is given here, value of the resistance is given here, value of the inductor is also given here, this resistance value is also given here. So again, it is the same approach here. First we try to find what is the steady state current in this inductor. Okay, once it is positioned out here, in this case this capacitor will be open circuit, and there will be no voltage across the inductor in steady state. So the voltage current flowing into this inductor will be 30 divided by 2 plus 1, they will come in series. Excuse me. So 10 amperes. So 10 amperes is the current which is flowing through this inductor, and also the voltage across the capacitor will be whatever is the voltage across the resistance, 2 ohms. Since there is no voltage across the inductor, you can use a potentiometer, or you can just multiply the current, since we have already found out the current, 10 amperes into 2 ohms, 20 volts. So this is the initial voltage across the capacitor. Now you are throwing this switch to position number 2. Now if you see, once you are throwing it into 2 position, this will become a parallel RLC circuit. Okay, so this is going to be a parallel RLC circuit out here, without an force response here. There is no external source now applied, because once it is thrown here, this goes out of the loop. Okay, so this is a parallel RLC circuit. To solve this problem, we can straight away use, although this derivation we have already done in the class, but once you remember these formulas, we will be able to directly get the solution. Okay, we know alpha, which is the damping ratio. For a parallel RLC circuit, it is 1 divided by 2 RC. Okay, now why this R has come in the denominator in this case is because a higher value of R, now the current would flow in the will not flow. If R is higher, current will not flow in this. There is a alternate path for current to flow through L and C, so the oscillations will sustain, and hence the damping will be slow. So that's why this R is in the denominator. Similarly, large capacitors will obviously store large amount of current, and hence it will take that much more time for the oscillations to die down. So that's why C is also in the bottom. So we directly find out alpha out here, and omega is 1 by root LC. That is the same whether it is parallel or series. This because LC is going to cause oscillations. So this formula remains the same. So once you know alpha and omega, we can write here in this case we can find alpha 1 and alpha 2 using the same old formula for S1 and S2. Okay, so here you got both these values to be negative, right? So S1 and S2 both are negative. So again it's written alpha 1 and alpha 2, but in our theory classes we denoted it as S1 and S2. So since both are negative, so this will be an overdamped case. Okay, so it is A1 e to the power of minus 1.5 t and A2 e to the power of minus 3t. So this straight away we can write this equation. Now we have to find out the value of the A1 and A2, right? So we need to take the initial condition, t is equal to 0, right? And I0 is known 10 ampere. So you get one relation between A1 and A2. Similarly, once that is known, we can write the voltage across L will be L di by dt. So this is the equation which is there. So I do di by dt, and then multiply it L, and that will be equal to the voltage across the capacitor, and the initial voltage across the capacitor we know is 20. So L is 2 here, and di by dt is this. So if you do that, you will get one more equation between A1 and A2. So solving these two, we get A1 and A2, values of A1 and A2. So the final equation from here, from this equation here on top, we are substituting the values of A1 and A2, and we get this equation out here. Okay, and since there is no voltage source here, the natural response itself is the final answer in this case. Okay. And then once that is the current which is there. Now to find out what is the voltage across the voltage across the inductor, we do L di by dt. So we can differentiate this and multiply it by L, and that will be the same voltage across the inductor also, across the capacitor also, because they are in parallel, right? So you get an VCT. Okay, and then the question says we need to find out what is the current in the capacitor also, expression for. So I is equal to C dV by dt, right? So the value of C is given as 1 by 9. So 1 by 9, and then you from here you differentiate once again, so you get this expression. So this is a simple way to solve these kind of problems. Okay, so this we will take one more last problem. In this it says for for Vt, we need to find Vt for t greater than 0. So assume the switch has been open for a long time. This is open for a long time, right? Now again we have to then it is closed out here. So if it is open for a long time, we need to find out the steady state. Okay, so obviously the steady state current in this will be 40 divided by 80 ohms, which is 0.5 ampere, and whatever is the voltage across 50 ohms will be 40 into 50 divided by 80, which we will get as 25 volts. Okay, so that is V0 is equal to 25 and I0 is equal to minus 5 ampere. And why we are writing it as minus 5 is because in the problem the direction of I is given like this. So that is the reason we are taking, because we know once this switch is in the open position, the current will flow in the opposite direction, starting from the voltage source through the 30 ohm inductor and then 50 ohm. So that is why we are writing it as minus 5 here. So once it is closed, once the circuit is closed, what happens is you again have a parallel RLC circuit. So this is shorted, right? So this 40 volt source and this 30 ohms, they'll be replaced by a short circuit. So you have a parallel RLC circuit, right? So now for a parallel RLC circuit, alpha is given 1 by 2 RC. So substituting these values, you get 500, and omega 0, which is the natural frequency, is given by 1 by root LC. So you get 354, right? So now this is the equation for finding S1 and S2. So you get two roots, S1 and S2. So both are negatives and both are real numbers. So it is an overdamped. So you have A1 e to the power of minus 854, and you get two equations. Now we need to find out what are the values of A1 and A2 comparing with the initial conditions, right? So if you see here, the initial this is the voltage equation, right? So this is the voltage equation. So for the moment you are switching it before whatever the initial voltage of the capacitor is 25, that t is equal to 0. So if I put t is equal to 0, this would go A1 plus A2. So I get A1 plus A2 is 25 out here, right? And then if I differentiate dV by dt, okay, into C will give the current. Okay, and now in this case, if you see here, the switch is closed out here. Okay, initially the current is flowing through 50 ohms through this inductor like this, right? Through 40, 30, 50. The moment the switch is closed, okay, the current is going to flow through this inductor, through this 50 ohms, and through the short circuit. So no current is going to immediately flow into this capacitor. Unlike in the previous case, there was no path for current to flow, so it was forced through the capacitor. But in this case, if you see, this switch is placed here, so whatever was the initial current, which will not start flowing through 20 ohm, okay, because this 40 and 30 has been replaced by a short circuit. So that current will flow in this loop out here. There is an alternate path available, so that current is not going to flow into the This is a parallel RLC circuit. Okay, so in a series RLC circuit, that initial current of the inductor will flow through the capacitor, whereas in this is the thing, more important thing which we need to remember. In a parallel RLC circuit, the initial current in the capacitor will always be 0, because you have a parallel path between R and L. So the current will flow in that loop, rather than that current will not be forced into the capacitor. Okay, so you have dV by dt as 0. Okay, that is the reason. So you put that values also. So you get one more equation. So solving this A1 and A2, for solving these two equations, you can find out what is the value of A1 and A2, which you can substitute in the in this expression which we got in the last page. If you substitute the values of A1 and A2, so we get the final expression. Okay, so that's all for today. Thanks a lot.